In the following moles and titration question taken from the ATP past paper, the question is basically around is about finding this element R in this compound RCO3. So what the question states is that a student is given a sample of a metal carbonate, which is RCO3, and she's then asked to determine the relative atomic mass of R and suggest its identity. So we need to find what this R is in RCO3. So starting with the first part A, you have the question states as a sample of the metal carbonate is added to a previously weighed container, which is then reweighed. So you're given the mass of the container plus RCO3 containing the carbonate, which is 12.01 grams, and you're also given the mass of the container. So the next part states is you're supposed to calculate the mass of RCO3 used in the experiment. So what you're going to do is you're going to subtract the mass of the container from this value 12.01, and you're going to get the mass of RCO3. So using my calculator, I'm going to do this calculation: 12.01 minus 10.97 grams. So the answer to that is it's going to be 1.04 grams. So that is the mass of RCO3, the metal carbonate. After which, moving to the second part B, the student transfers the sample of RCO3 to a beaker and adds 50 cm3 or 1 mole per decimeter cube of hydrochloric acid. So this sample is transferred to a beaker, and then 50 centimeter cube of 1 mole per decimeter cube of hydrochloric acid, which remember is in excess, is added. So I'm going to draw a rough sketch showing that. So here is my beaker, and let's put 1.04 grams of this carbonate. So you have 1.04 grams of RCO3, and I'm adding hydrochloric acid. I'm adding 50 cm cube of 1 mole per decimeter cube of hydrochloric acid, so that's being dissolved in hydrochloric acid. So this is HCl, aqueous, and remember it is in excess, and the volume and concentration are given. So it's 50 centimeter cube, and the concentration is 1 mole per decimeter cube. So we know the concentration of HCl that's being added as well. And remember that this HCl is in excess. So you're adding excess HCl, which means that at the end of the reaction, when these two react, a carbonate is reacting with hydrochloric acid. Once this reaction is complete, HCl, there would be some leftover HCl still in the flask. So in the next part of the question states that all the solid reacts to form an aqueous solution, which means that this carbonate reacts with the HCl. So we can come up with an equation of a carbonate reacting with hydrochloric acid. So it's RCO3, and based on the formula we can figure out that R has a charge of +2 because CO3 has a charge of -2. So I'm going to write a reaction. It's reacting with HCl, and it's going to produce salt, water, and carbon dioxide. So the formula of the salt would be RCl2. Remember that R is +2. Plus you're going to get carbon dioxide, which is CO2, and you're also going to form H2O, and to balance this equation there should be 2 HCl molecules. So he's saying that all of the carbonate reacts and ends up producing this salt, so it forms an aqueous solution. And when the reaction has finished, the contents of the beaker are transferred to a volumetric flask. So there would be some leftover HCl because it's in excess. So the solution would contain two things. One of them would be the salt that is formed, which is RCl2, plus the water and carbon dioxide. Carbon dioxide bubbles would escape, so you're going to notice bubbles of carbon dioxide gas escaping. But there would be some leftover HCl in the solution as well at the end of the reaction. So these are the two things that would be part of the solution at the end of the reaction once all the carbonate RCO3 has reacted. So he's saying this when the reaction had finished, the contents of the beaker are transferred to a volumetric flask. So we're now going to transfer the solution to a volumetric flask, and where the solution is then made up to 250 cm3 by adding distilled water and mixed it well, and this is called solution S. So let's sketch that part as well. So I'm going to transfer this solution, the leftover part of the solution, into this volumetric flask. So all the HCl which was in excess, that was leftover, is transferred to this flask along with this salt which is formed. And this is made up to 250 cm3. So this volumetric flask is going to have a 250 cm3 mark, and I'm going to mix distilled water into it, and make a solution that has a volume of 250 centimeter cube. So now we have a 250 centimeter cube solution, and the name of the solution is S. This is solution S, and remember that it contains the leftover excess HCl. So it contains the excess HCl plus all the salts that were formed in the previous reaction, which I don't think are going to take part in the reaction because they've already been formed. So I think the rest of the reaction would be with the excess HCl, the leftover HCl that's present in this solution. Now in the next part, using a pipette, 25 cm cube of S is transferred to a conical flask and a few drops of methyl orange indicator are added. So we're using a pipette to transfer this 25 cm cube of S that we have made to a conical flask. So this is the solution S that we made up by adding distilled water to the leftover in the first reaction. So that's a 250 cm cube solution S. So I have a conical flask over here, and I'm going to transfer 25 centimeter cube of S. So only 25 centimeter cube. Remember, the original solution S has a volume of 250 cm cube. So I have transferred 25 cm cube of S into this conical flask over here, and also another part of the statement was that a few drops of methyl orange indicator are added. So we are adding a few drops of methyl orange as well. So there is going to be methyl orange indicator, just a few drops. So that's also being added. Remember that S contained the excess HCl. It had the leftover HCl in it. So remember what S was. S was the leftover of the first reaction. Whatever that was left in this first reaction, you're adding excess HCl. So some of the HCl was left behind. You put it in. You transfer that into this volumetric flask and made a 250 cm cube solution by adding distilled water, and that was called S. And then this S was then transferred to this conical flask over here, so it still contains that HCl, and with methyl orange in it, a few drops of methyl orange are added. So the next part of the question is next part of the question is that a burette is filled with 0.1 mole per decimeter cube of aqueous NaOH, which is then added to the conical flask. So we're going to do this part now. We have a burette which contains NaOH, and it is added to the conical flask until an end point is reached. So we are doing a titration. So I'm going to draw a burette over here. So this is my burette, and I'm going to fill it with NaOH, and the concentration that was mentioned for NaOH was 0.1 mole per decimeter cube. So the concentration of NaOH is known. It's mole per decimeter cube. So that is present in the burette. NaOH, HCl is present in this flask, and we're going to start titration. We're going to add NaOH drop by drop. So when we add NaOH drop by drop, the HCl in the flask is going to get neutralized. Remember that methyl orange has red color in acid, and it is orange yellow in alkaline conditions. So the next part is asking us what is the color of the solution in the flask before the alkali is added and at the end. So before the alkali is added, this methyl orange is present. It is in a solution that is acidic because it has HCl in it. So methyl orange would initially be red in color. So initially methyl orange would be red in color, but once the acid gets neutralized by the alkali NaOH that is being added, all the HCl is going to react eventually, and all the HCl is going to get neutralized. And if you add too much of NaOH into this flask, the solution would eventually become alkaline, and once it becomes alkaline, the color would change to orange or yellow. It's going to change to orange yellow. So that would be the color change before and after the alkali has been added. So we're going to write that down. Before the alkali is added, it's going to be red in color. Once it has been neutralized, all the acid has been neutralized and alkali goes in excess, it's going to turn orange yellow. That would indicate that we are now adding too much alkali, so we need to stop the titration. Now in the next part, part C, we're given the titration results, and the student does 3 titration, and diagram below shows part of the burette with the liquid levels at the beginning and end of each titration. So we were doing this titration at the end where we were adding NaOH to the excess HCl solution S, 25 cm³ of S, and we were reacting the two together. So he's given us three different readings, three different experiments are done. Remember, experiments are done to improve the accuracy of the result. So three different titrations are performed to get better, more accurate results, because if you average values, you get more accurate results. So the amount of NaOH that's being added, we're now going to calculate and find out how much NaOH was actually added from the burette. So you're given three titration readings, three different experiments, and you're given the initial and the final burette readings for each one of them. So we're going to start filling this table, which is shown over here, and filling this table, I'm going to first write down the initial burette reading for the first titration, which is 0.00 cm³, the one that is shown over here. And once the reaction titration had finished, the final burette reading was 25.90 cm³. So we're going to find out what is the amount of NaOH that was used. It's going to be the difference between the two values, which comes out to be 25.90 cm³. So that is the amount of NaOH that's used in the first titration. Moving to the second titration, the experiment is repeated, and the initial burette reading shows 23.3 cm³. So that's 23.30 cm³. The final burette reading is 48.40 cm³. And now we're going to find out what is the amount of NaOH that has been added. It's going to be the difference between the two values. And this comes out to be 48.40 minus 23.30 comes out to be 25. It comes out to be 25.10 cm³. Remember to take burette readings to two decimal places, because that's the accuracy of the equipment. Burette has an accuracy of 2 decimal places. Moving to the third titration, filling in the values, the initial titration reading shows 6.90 cm³. So that is 6.90 cm³, and the final burette reading shows 32.20 cm³. Taking the difference using my calculator, it's going to be 32.20 minus 6.90, and the answer is 25.30 cm³. So we've got three titration values. In the first experiment, 25.90 cm³ of NaOH was used. In the second experiment repeated, it shows 25.10, and in the third experiment, the amount of NaOH that's being added into the flask is 25.30. Now we have to tick the best titration results, and the best titration results are the ones that would be close together. So this first value is slightly off. It's further away from the other two values. So this one is slightly anomalous, which means that there must be some error in this experiment. These two values are close to each other, which shows consistency. So we're going to select these two values. These two values appear to be more accurate and more consistent. And in the next part, we have to calculate, using these results, calculate the average volume of 0.1 mole per decimeter cube of NaOH. So we've gotten two values for two experiments. So we're going to take the average of the two values, which is going to be 25.10 plus 25.30, and we are going to divide that by 2. So my average volume of NaOH that's been used in this experiment is going to be 25.20 centimeter cube. So that's the average volume of NaOH, and we're going to add that over here as well. The amount of NaOH that's been used, the average volume of NaOH that's been used is going to be 25.20 centimeter cube. Now, if you look carefully, we already knew the concentration of NaOH. Now we also know the volume of NaOH that's been used. So in the next part, part D, we are being asked calculate the number of moles of NaOH in the average volume of 0.1 mole per decimeter cube of sodium hydroxide. So the 0.1 mole per dm cube NaOH, we also know the volume. So for solutions, the formula is that moles is concentration multiplied by volume. And we know the concentration. The concentration of NaOH is 0.100. And we also know the volume of NaOH, which is 25.20 centimeter cube, which we found from the titration. experiments, 3 titration experiments that we did. So it's going to be 25 point, we're going to multiply that by 25.20, which is our volume, but that should be in dm cubes, so we are going to divide that by 1000, and the answer that we're going to get is 0.00252 moles. So that is the amount of moles of NaOH that are being added. So I'm going to add that over here as well. So the amount of moles of NaOH are 0.00252 moles. So that is the amount of NaOH that is being added from the burette into this flask, which contains the leftover HCl. So in the next part, part E, you're now asked, using the equation that NaOH plus HCl produces NaCl and H2O, calculate the number of moles of hydrochloric acid in 25 cm cube of S. So 25 cm cube of S is this thing over here. And according to the equation, 1 NaOH reacts with exactly 1 HCl. So the ratio in which NaOH and HCl react is 1:1. So if so the amount of moles of NaOH and HCl are going to be exactly the same. So going back to our sketch over here, if NaOH has 0.00252 moles, then HCl is going to have exactly the same number of moles, because the ratio in which NaOH and the ratio in which HCl react is exactly 1:1. So the next answer is going to be exactly the same. It's going to be 0.00252 moles, because NaOH and HCl react in exactly the same ratio. Moving to the next part F, you're now asked to calculate the number of moles of hydrochloric acid in 250 cm cube of S. So what we have done is we've been able to find the moles of HCl in this flask over here, which were 0.00252 moles. And remember that we just took 25 cm cube of S. So these are the moles in 25 cm cube of S. It's 0.00252 moles. Now he's asking us to find the moles in this 250 cm cube of S that we originally made. This was the solution that we made, which contained the excess HCl. We only used 25 cm cube of S in the titration. So if you had 0.00252 moles in 25 cm cube, so what were the amount of moles in the original 250 cm cube solution? So again, we're going to use ratios. The ratio is that we know that in 25 cm cube solution S, the amount of moles that we have are 0.00252 moles. So what are the moles in 250 cm cube of the original solution that we made, solution S? So that would be X moles. So using the crisscross method, it's going to be X would be equal to 250 divided by 25 and multiplied by 0.00252, and the answer is going to be 0.0252 moles. So that is basically, it basically means that in 25 cm cube you had these many moles. So in 250 cm cube the amount of moles is going to be 10 times that value. So we have found the moles of HCl in this 250 cm cube solution as well. So that is 0.0252 moles. So that's the amount of moles of HCl present in this flask in the solution that we made using distilled water. Now remember one thing, that this HCl is the leftover HCl from the previous reaction. In the previous reaction, the original reaction that we did, we added an excess of HCl was added. It was 50 cm cube, 1 mole per dm cube, and this excess HCl, not all of it reacted in this first reaction. This leftover HCl was then transferred to this volumetric flask. So this is the leftover HCl from the previous reaction. So now he's asking us in part G, calculate the number of moles of hydrochloric acid in the original 50 cm cube, 1 mole per dm cube hydrochloric acid. Now he's asking us the moles of HCl that we added initially that we added. So we're going to use the formula, which is moles in a solution are basically concentration multiplied by volume. The concentration is known, it's 1 mole per decimeter cube, and the volume is 50 centimeter cube, and we're going to divide that by 1000. and the answer is 0.05 moles. So these are the moles of HCl that were originally added. So again, look at the diagram carefully. These are the moles of HCl that were originally added, and these are the moles of HCl that are left over in the flask at the end of the reaction and that were transferred into this volumetric flask. So what is the amount of HCl that reacts with this? So 0.05 moles are originally added, 0.0252 moles are left at the end of the reaction, which means if we take the difference of the two, that is the amount of moles that were used up in this first reaction over here. So in the next part, this is the very thing that he's asking. He's asking, by subtracting your answer in F from your answer in G, calculate the number of moles of hydrochloric acid that react with the sample of RCO3. So originally we added 0.05 moles, and at the end of the day we had 0.0252 moles of HCl still present, unreacted. So we're going to take the difference in the moles of the two values. So it's going to be 0.05 minus 0.0252, and the answer I'm going to get is going to be 0.0248 moles. So that is the amount of moles of HCl that's actually reacting with this carbonate in this original reaction. So that is the moles that are originally reacting. So what I'm going to do is on my sketch over here, I'm going to cut out 0.05 because that's not actually reacting. So I'm going to write 0.0248 moles instead, because 0.05 moles was in excess. They were not reacting because 0.0252 moles were left over at the end of the reaction. So the amount of HCl that's actually taking part in this first reaction with RCO3 are 0.0248 moles. Now moving to the next part, we found the amount of moles of HCl that are reacting with RCO3, which are 0.0248 moles. So now he's asking, calculate the number of moles of RCO3 that react with the number of moles of hydrochloric acid. So we know the moles of HCl that are reacting with RCO3. We now need to find the moles of RCO3. So according to this equation, the ratio in which they're reacting is 2:1. So it's 2 HCl's react with 1 RCO3. So if you had 0.0248 moles of HCl, what would be the amount in moles of RCO3? So we're going to use ratios and applying the crisscross method. Using the unitary method, x would come out to be equal to, it would be 0.0248 divided by 2, which is going to be 0.0124 moles. So that is the amount of moles of RCO3 present in the original sample. And the next part now is going to ask, using your answer to A and I, calculate the relative formula mass of RCO3 and hence the relative atomic mass of R. So we first need to find the MR, or formula mass, of RCO3. We have the moles. We know that RCO3, the quantities that we have for RCO3 are the moles. We know that we are using 0.0124 moles of RCO3 in a reaction, and we also have the mass. We initially, when we started off in the very beginning, we calculated the mass of RCO3 that we were using in the reaction, which was 1.04 grams. So we also have the mass of RCO3, which is 1.04 grams. So you have the moles, you have the mass, you can find the MR, because moles, 0.0124 moles is equal to mass, which is 1.04 grams divided by MR. So using the formula moles is equal to mass over MR, we can find MR. Rearranging the terms, it's going to be 1.04. So it's going to be 1.04 divided by 0.0124. And this comes out to be equal to approximately 84. So that is our approximate relative formula mass of RCO3, the MR of RCO3. It comes out to be approximately equal to 84. And the next part is we need to find the relative atomic mass of R. So what we're going to do is, I'm going to just get rid of this CO3, the AR of C and 3 oxygens from 84. So 84 is the total MR of this entire thing. So if we remove the carbon, that's 12. And if we remove 3 oxygens, So that is 16 into 3. So if we get rid of that, then we are left with R, which is going to be equal to 24. So the relative atomic mass of R, this element R, is 24. And now what we need to do is that R is less reactive than calcium but more reactive than zinc. Suggest the identity of R. Now since you know the relative atomic mass of R, you don't even need to know this information. You just go in and have a look at the periodic table and figure out which element has an atomic mass of 24. So this information is just to confirm the element that you find. The element that we will locate in the periodic table having an AR of 24 is going to be Mg, magnesium. And this information fits exactly with that because Mg is less reactive than calcium. If you look at the reactivity series, Mg is less reactive than calcium and it's more reactive than zinc. If I write down the reactivity series, potassium, sodium, calcium, then there's Mg, then aluminium, then zinc. So Mg over here is less reactive than calcium and it's more reactive than zinc. So the correct answer for this part is going to be magnesium, and that's going to solve your question. We have been able to find the identity of R.